Hello, so we will start with our lecture discussion on modern physics. So, as an overview, um, at the end of the 19th century, many scientists believed they had learned most of what there was to know about physics. Newton's laws of motion and theory of universal gravitation, Maxwell's theoretical work in unifying electricity and magnetism, the laws of thermodynamics and kinetic theory, and the principles of optics were highly successful in explaining a variety of phenomena. At the turn of the 20th century, however, a major revolution shook the world of physics. In particular, in 1900, Max Planck provided the basic ideas that led to the formulation of the quantum theory, and in 1905, Albert Einstein formulated his special theory of relativity. Both theories were to have a profound effect on our understanding of nature. Within a few decades, they inspired new developments in the fields of atomic physics, nuclear physics, and condensed matter physics. So, in our first chapter, we shall introduce the special theory of relativity. So, this theory provides us with a new and deeper view of physical laws, although the predictions of this theory often violate our common sense. The theory correctly describes the results of experiments involving speeds near the speed of light. We will cover the basic concepts of quantum mechanics and their application to atomic and molecular physics. In addition, we will introduce solid state physics, nuclear physics, particle physics, and cosmology if time permits. Even though the physics that was developed during the 20th century has led to a multitude of important technological achievements, the story is still incomplete. Discoveries will continue to evolve during our lifetimes, and many of these discoveries will deepen or refine our understanding of nature and the universe around us. The special theory of relativity. Before we delve deeper into the special theory of relativity by Albert Einstein, we shall recall Newtonian or the classical relativity first. So, in classical relativity, we have this assumption that Newton's laws of motion must be measured with respect to or relative to some reference frame. And a reference frame is called an inertial reference frame if Newton's laws are valid in that frame. So such a frame is established when a body, not subjected to net external forces, is observed to move in rectilinear motion at constant velocity. That means to say that frame is not accelerating. Now, if Newton's laws are valid in one reference frame, then they are also valid in another reference frame moving at a uniform velocity relative to the first system. So this is referred to as the Newtonian principle of relativity or the Galilean relativity. So consider two inertial frames. We have uh, K and K prime. K is at rest and K prime is moving with velocity v towards the positive x, x prime axis, and their axes are parallel. K and K prime are said to be inertial coordinate systems. So they are both inertial coordinate systems. Remember that K is at rest while K prime is moving with velocity v away from K. So both of them are inertial coordinate systems. Now, here is the Galilean transformation. So for a point P, um, we can say that in system K, P can be found at x, y, z, t. And in system K prime, P or point P can be found at x prime, y prime, z prime, and t prime. Now let us see how are these um, coordinates related. So take note that k and k prime have parallel axes, and k prime has a constant relative velocity in the x direction with respect to k. Therefore, your x prime can be expressed in terms of x. So we have x minus the speed of k, or the velocity, the relative velocity of k prime with respect to k multiplied by the time t. And then you have y prime is just equal to y, z prime is just equal to z, and t prime is just equal to t. So in the Galilean transformation, time t for all observers is a fundamental invariant that is the same lang siya for all inertial observers. So that is for the Galilean transformation. Now for the inverse relationship, um, replace v with negative v, and you have to replace the primed quantities with the unprimed, and the unprimed with the primed. So let us go back to our previous slide. So we have this Galilean transformation expressing the primes in terms of x, y, and z, t. So we have here x is equal to x prime plus bt, y equals y prime, z is equal to z prime, and t is equal to t prime. So this is for the inverse relations. Now, although Newton's laws of motion had the same form under the Galilean transformation, Maxwell's equations did not. So in 1905, Albert Einstein proposed a fundamental connection between space and time, and that Newton's laws are only an approximation. By the end of that amazing year, he had published three papers of extraordinary importance. One was Analysis of Brownian Motion. A second, for which he was awarded the Nobel Prize, was one of the photoelectric effect. In the third, Einstein introduced his special theory of relativity, proposing drastic revisions in the Newtonian concepts of space and time. The special theory of relativity has made wide-ranging changes in our understanding of nature, but Einstein based it on just two simple postulates. What are these postulates? So one states that the laws of physics are the same in all inertial frames of reference, and the other states that the speed of light in vacuum is the same in all inertial frames. These innocent sounding propositions have far-reaching implications. So here are three implications. The first, events that are simultaneous for one observer may not be simultaneous for another. Second, when two observers moving relative to each other measure a time interval or length, they may not get the same results. And lastly, for conservation principles for momentum and energy to be valid in all inertial systems, Newton's second law and the equations for momentum and kinetic energy have to be revised. Relativity has important consequences in all areas of physics, including electromagnetism, atomic and nuclear physics, and high energy physics. Although many of the results derived in this particular chapter may run counter to your intuition, the theory is in solid agreement with experimental observations. Okay, let us take a look at the two postulates that make up the special theory of relativity. Both postulates describe what is seen by an observer in an inertial frame of reference. Again, an inertial frame of reference is one in which an object is observed to have no acceleration when no forces act on it. And furthermore, any frame moving with constant velocity with respect to an inertial frame must also be an inertial frame. So Einstein's first postulate is the principle of relativity, which states that the laws of physics are the same in every inertial reference frame. So for example, uh, let us take a look at the electromagnetic force induced in a coil of wire by a nearby moving permanent magnet. In the frame of reference in which the coil is stationary, the moving magnet causes a change of magnetic flux through the coil, and this induces an EMF. In a different frame of reference in which the magnet is stationary, the motion of the coil through a magnetic field induces the EMF. According to the principle of relativity, both of these frames of reference are equally valid. Hence, the same EMF must be induced in both situations. And this is indeed the case. So, Faraday's law is consistent with the principle of relativity. Indeed, all of the laws of electromagnetism are the same in every inertial frame of reference. During the 19th century, most physicists believed that light traveled through a hypothetical medium called ether, just as sound waves travel through air. If so, the speed of light measured by observers would depend on their motion relative to the ether, and would therefore be different in different directions. So there is an experiment conducted, the Michelson-Morley experiment. It was an effort to detect motion of the Earth relative to the ether. Einstein's conceptual leap was to recognize that if Maxwell's equations are valid in inertial frames, then the speed of light in vacuum should also be the same in all frames and in all directions. In fact, Michelson and Morley detected no ether motion across the Earth, and the ether concept has been discarded. Although Einstein may not have known about this negative result, it supported his bold hypothesis of the constancy of the speed of light in vacuum. So, Einstein's second postulate states that the speed of light in vacuum is the same in all inertial frames of reference, and it is independent of the motion of the source. Now let's think about what this means. Suppose two observers measure the speed of light in vacuum. One is at rest with respect to the light source, and the other is moving away from it. According to the principle of relativity, the two observers must obtain the same result, despite the fact that one is moving with respect to the other. Now, if this seems too easy, let us consider the following situation. A spacecraft moving past the Earth at 1,000 meters per second fires a missile straight ahead with a speed of 2,000 meters per second relative to the spacecraft. The question is, what is the missile speed relative to the Earth? Now, according to Newtonian mechanics, the correct answer is 3,000 meters per second. But now, suppose the spacecraft turns on a searchlight pointing in the same direction in which the missile was fired. An observer on the spacecraft measures the speed of light emitted by the searchlight and obtains the value of c, which is equal to 3 times 10 to the 8th meters per second. According to Einstein's second postulate, the motion of the light after it has left the source cannot depend on the motion of the source. So the observer on Earth who measures the speed of this same light must also obtain the value of c, not c plus 1000 meters per second. This result contradicts her elementary notion of relative velocities, and it may not appear to agree with common sense. Einstein's second postulate immediately implies that there is an ultimate speed limit. So it is impossible for an inertial observer to travel at c, the speed of light in vacuum. We can prove this by showing that travel at c implies a logical contradiction. Suppose that the spacecraft is moving at the speed of light relative to an observer on the Earth, so that the velocity of the spacecraft with respect to the Earth is equal to c. If the spacecraft turns on a headlight, the second postulate now asserts that the Earth observer measures the headlight beam to be also moving at c. Thus, this observer measures that the headlight beam and the spacecraft move together and are always at the same point in space, which is absurd. But Einstein's second postulate also asserts that the headlight beam moves at a speed c relative to the spacecraft, so they cannot be at the same point in space. This contradictory result can be avoided only if it is impossible for an inertial observer, such as a passenger on the spacecraft, to move at the speed of light.